Hey, hi everyone. Today we will look at in this session the verification overview, and let's go to the agenda. So, as a part of today's session, we will first look at verification from the point of view of what all of us have experienced. It's very important to when we start learning a new topic, it's very important that we connect to something that all of us have experienced, and then use that as a the jumping board for diving into a new area. That way, it makes the process of understanding something new easier. So we will look at one of those examples, and then using that example, we will define the process of verification, and as a part of that process of verification, you will be able to see that we have three phases. So those three phases are: we have a planning phase, and then we have a development phase, and then we have a regression phase. So we will look briefly into each of these phases as to what are these phases composed of and what activities are done, and then we'll briefly look at like a verification team composition. This is primarily meant to give you an idea of what type of different types of expertise that you can build over a period of time to grow in your career. And then we'll briefly look at what are the different types of verification that are performed typically, and then we'll close the session with the trends that are emerging in the current verification. So let's jump into it. Uh, Here we are looking at, we may not, like, not all of you might have done all the big designs, but all of you would have gone through digital design course, and as a part of that course you would have realized various sequential as well as combinational circuits. And in order to do that, you would have taken these standard IC packages, like let's say this 7408, which is a 4 2-input AND gates. And the way you would have performed the process of your lab would be that you would plug in this particular IC into a breadboard, you'll power it up, and then you will take the truth table that's present on this right side, and let's say there are two inputs to this particular, you'll pick each of the gate, and that gate will have two inputs and an output mapped to some pins, and you will use the wires to go through all these four combinations of 0 0 0 1 1 0 1 1, and check that the corresponding output matches the expectation by looking at some LED or on a oscilloscope. And this process, only after you do this process with all the components that you have collected, by making sure that each one of them is operational, is when you would have actually realized your final circuit. And this is nothing but the fundamental process of verification, that you have the specification and you are looking at all possible inputs that can be given to a particular design, and you have the understanding of what is expected, and you are providing those inputs to your design and checking whether the output matches the expectation. So this fundamentally is nothing but is the process of verification, that you provide certain stimulus and check that it matches the requirements. And this fundamental concept that the verification is all about the stimulus generation and response checking, I would say that we should all visualize it as a goggle, and then anytime a requirement specification is given to you for verification, you imagine this goggle on your eyes and look at every line in the specification from the point of view of what stimulus do I need to generate to exercise this particular design, and how do I check that for the given stimulus the design is behaving as per the expectation. So this, the way we did it manually, it's okay, right? So we can do that for some simple designs, but when we build a complex ASIC, right, in a project, you can imagine that it will not be built in one day, right? So as we could get the components in the lab, it's not, because you are building now those components and those are pretty complex, they're not available, and it is being designed as RTL, right? So and those RTL will go through a lot of changes every day, and then every time it goes through the change, now we cannot perform the process of like providing all possible input stimulus and checking whether it's performing correctly manually, right? I mean, like, you can imagine that a particular design may go through more than 30 times. It could be changed into, or it could be enhanced, or it could be bug fixes. So every time a design changes, we cannot repeat the process, and repeating this process of generating different stimulus and seeing whether it is performing correctly is important, because after every change, because there is a relation that could exist between different features, that we think that something had passed, and then after a change, that particular feature may no longer be operational, and it could be it could have broken because of change in another feature. So we cannot say that we will not repeat the process. We will have to repeat this process of generating the stimulus and doing the checks. Now, how do we repeat this process, right? How do we repeat it such that such that it is not manual? Because if we repeat it manually, what happens is that it takes a lot of time, first thing, and the second thing is that anything that we do manually is highly error prone, right? And then if different people have to repeat it, there may not be a consistency in the way that particular process is done, and anything that is sort of is manual and error prone and takes longer time is not something that you want it in your ASIC design cycle. So that's why you need something that is which is very automatic, so that we can repeat it faster, and because it's automated, it is less error prone. So we need such a system. And what could be such a system that we have already experienced? Let's look at it. Yes, this is a digital IC tester. Some of you might have seen it. Let's understand how this works, and we will use this as a basis to define what are the expectations from the test bench. So here there will be a slot or the interface where we can plug in the IC, and then through this keypad we can enter the configuration, like let's say 7408, and then there will be a start button, and once I press the start button, this digital IC tester will apply all possible input stimulus combination to this particular IC. It will go through a series of tests, and then at the end of the test it will display whether this particular IC has passed the test or failed the test, right? So what we need for complex ASICs is something similar to this, that can take in a complex ASIC design and provide all possible stimuluses, do the checks on the output whether they are matching the expected one, and at the end of the test tell us whether the test has passed or failed, right? So essentially two things, right? One is generate all possible combinations of inputs and check the output. That's one part. And second, being able to automatically repeat it, the similar type of steps again and again more efficiently, right? So across all the tests, that's what we need. And that whole setup in the verification world is called as a test bench, and those test benches are built using either like a Verilog, or now currently using the high level verification languages such as SystemVerilog. Now what we will do is, as a part of next step, whatever the process of verification that we have seen so far, let's formalize it a little bit so that we can develop it in a way that can be applied to more real complex ASICs. Okay, so the process of verification, if we look at it, what happens is it always begins with the requirements, right? So we have a certain requirement, like let's say I want to build a SoC to meet let's say edge computing requirement, or let's say even at a simplest level I want to build an IP that satisfies a PCIe Express port or a USB port or something like that, right? So that is my requirement specification, and these requirement specifications could be like coming from a standard spec bodies, like as I talked about, it could be Ethernet, it could be PCIe, it could be USB, it could be MIPI protocols, which are standard, or it could be something proprietary, right? Like somebody could be building proprietary image processing algorithms or some GPUs. So it could be some proprietary, but at the core of it, there will be some requirements that will be present, and the logic needs to be designed as per those requirements, right? So on one end of the process, on the left side, there will be a design. So design is nothing but the transformation of these requirements into a RTL design. So basically we have to understand that the requirements are being transformed into a design, right? So that is what we are doing on the design side. We are reinterpreting it in a requirement in the form of like, okay, I am issuing, we need a way in which, like, when we are providing, let's say, certain form of stimulus, it should not it should not overflow, right? So that could be like a very high level requirement, and the microarchitecture could have been defined as, okay, that should be implemented through a set of ready valid signals, and you assert a valid, and then the ready, up to the ready comes, it should not send the data, so that way there is no data loss. So a high level requirement is transformed into signal level interaction. That is the process that is happening when we are doing the design. So we're taking a requirement and translating into the language that is understood by the design. On the right hand side, we do the same process. That's the common requirements that we were using for the design. Now we are using for defining the test bench, right? So we use that requirements to define the test bench, and the test bench is the view of the application world around the design, right? So that is what it is. Like as we saw in this particular in the previous slide, right, that our digital IC tester was able to apply the different inputs, right? So similarly, the test bench will hold the design, and it will be able to apply the different, it will provide a mechanism through which we can apply different possible inputs to this design. And the capabilities of this test bench are used by the test suite. So there will be various tests that will be built, and each one of them will utilize the capabilities of this test bench, which is the environment surrounding your design, meeting the same requirements, and it will be able to exercise a design in different scenarios and check whether the output is matching the actual expectation. When all of them pass, we say that it has met the requirements, right? So we started with requirements. Requirements are translated into design. Requirements are translated into a form of verification. When we say verification, we have already seen it's nothing but in the form of what is the stimulus that we are generating and what is the checks that we need to do. And this test bench is an environment that makes it easy, that provides you all the abilities to be able to do that, exactly similar to the digital IC tester that we saw in the previous slide. And the test suite uses the capabilities to perform different scenarios, the complex interaction between various features, and we run this test suite to test all the flavors and the configurations of the design. And once all of that is done, we say that whatever we started off with has been met, and hence the process of verification is complete. See, in the previous slide we looked at the process of verification. Now let's introduce few more practical things into it. So we have languages and we have methodologies, and let's understand in this overall process of verification what remains constant, what changes, and how it gets adapted to different languages and the methodologies. So in the previous slide we saw that we were translating the requirements into verification requirements, building test bench out of it, and we created multiple tests and we executed them, and we got them to the passing state, right? So that's a basic verification process. Now if we look more closely into it, right, so it essentially consists of three phases. There is a verification planning phase, and then there's a test bench development phase, and a regression, debug, and a sign off phase. These are the three phases that are part of your process of verification. And as a part of verification planning, right, there are two key things that gets created. One is your actual verification plan, which consists of typically a test plan, checks plan, and a coverage plan. and using those three plans you come up with a test bench architecture. So those two are the key requirements to proceed to development phase. So once you have created those two plans, you create, based on that you create a schedule, and then you move on to the test bench development. And in the test bench development, you pick a particular language that you want to implement the test bench, and then you pick up a particular methodology, and you go ahead and either reuse some of the test bench components or build some new components and put them together and create the test bench and the test suite. So that's what you do in the test bench development phase. And once the test bench is ready to certain extent and the design is ready to certain extent, you put them together and start enabling features one by one, right? And the main key focus of regression phase is that as the features evolve, as we talked about it briefly, one feature is going to have impact on another feature. So we want to make sure that what has passed remains in a passing state, and if it fails, we want to detect it as soon as possible so that we can find out a fix for that. So in the regression phase, you get few tests passing and try to keep them passing while enabling the newer features. And so you, whatever fails, you debug it, and then once you have gotten to a reasonable level of stability in terms of your pass rate from your overall test suite, you move on to the sign off phase. And in sign off phase, you look at various metrics to make sure that really the process of verification has come to a point where it is satisfactory. It never really closes, but it is satisfactory, and you tape out your chip, right? So that's the broadly the phases. And now if we look at it, we can use various languages, right? And this slide, the message that it is trying to communicate is these two components are separate. That is, the process of verification remains more or less same irrespective of the choice of language or methodologies. It's not completely independent, but a good part of it in principle remains same. Like for example, if I were to execute the process of verification using Verilog or a VHDL, then what happens is these languages do not have a very good support for randomization. So I might rely on fewer random test cases and more directed test cases. That's what I will have to do if I have to rely on this. Because if I try to implement more and more complex randomization, then it doesn't make sense for me to continue with Verilog and VHDL, because the complexity of implementing them will be so much that I would rather move on to the SystemVerilog. But when you move on to the SystemVerilog, then what it means is you can now tune the process of verification to rely on more on randoms rather than on directed. But the principle again remains same. And if I were to do the process of verification for, let's say, only one IP, and that IP is not changing much, I don't even really need methodology, because methodology is required if you are doing multiple IPs and you want to optimize and reuse across your IPs, and also those IPs keep changing a lot, and your test bench needs to adopt, then you need a methodology to take care of the reuse part of it. So I will use the SystemVerilog along with some methodology to satisfy that particular requirement. And recently, if you look at it, the languages like Python along with the CocoaDB is coming up, which shows that like a very general purpose language like a Python can also be used for executing the process of verification. So the key message over here is two things. One is, when we looked at the process of verification, it consists of three phases: your planning phase, development phase, and regression debug, coupled with the sign off, which in principle remains independent of the language and the methodology that you choose to do it. And the language and methodology, they don't completely change, but the process of verification can be tuned to extract or exploit the strengths that are present in the language and the methodology to achieve the objectives better for which whatever the language and methodology that you have chosen. So I hope that point is clarified. So in the last two slides, we have looked at and we have defined the verification process. So in this slide, let's define how is the implementation of the verification process is done. And we will look at what happens in each of these phases, what are the key things, key activities in each of these phases. So we have already looked at it, that we have a planning phase, and in the planning phase we create these three plans. We create the test plan, we create coverage plan, and we create checks plan. And then we create the test bench architecture, which is satisfying all these three plans that we have created. And based on the test bench architecture and the overall three verification plan, we create the task lists. The task list to build this test bench and to create all the tests on the top of that test bench. And then what we do is, all the task lists that we have created, we map them to different milestones. So a design verification project that is executed consists of various sub milestones before the final tape out happens, and those sub milestones are also aligned to various backend activities that takes place, where they snap different net lists of different completeness of design to do their steps. So it's kind of aligned, so multiple teams get aligned. And so we need to map this task list to this milestone, so that whatever the development or whatever the verification we are completing is in alignment with all the teams, because everyone has to meet their own requirements. So that is what happens in the planning. And once you have this milestone map task list, you go to the development phase, and in the development phase you start like building the test bench. And that starts with, like, you build BFMs, you build the test bench, you create the tests. And we use this concepts of object oriented programming for building the test benches. However, the way we use object orientation in verification is slightly different than the way we use it in the typical software world. If you have already used it, this is going to be slightly different, and how it is different we will see it further. And along with that, we will be using the high level verification languages and its features, the SystemVerilog features. Then there is a methodology like UVM that gets used, and there are a lot of repetitive items that are being done as a part of development phase, and as well as part of the regression phase, that are handled with the help of the scripting, which is done either in Python, Perl, or Shell. So that is handled in this part. And so once you have done, let's say, about 50 to 60% of your test bench development, and we have enabled few features, you move to regression phase. So what happens in your regression phase is that you have certain features working, and you're trying to enable new features, and anything that you're enabling the new feature can affect your existing passing feature and can make them failing. And if at all that happens, what you want to do is, you want to detect that early and want to get a handle on that as soon as possible, right? So that's what you are essentially trying to do in the regression phase. And in order to do that, you come up with various strategies. So one of the strategies is, let's say, you create a check-in regression. So check-in regression is a subset of tests that you will run before committing any code changes, right? So because as I mentioned, we have come to like a 50 to 60% completion point. So let's say I have about 40 tests passing, right? So now if I make any changes in either the test bench or the design, what I want to do is, I want to run a subset of those 40 tests. So let's say those 40 tests are organized in 4 categories of 10 tests each. Then what I might do is, I might pick 1 or 2 tests from each of these categories and run those 4 or 5 tests every time I do the changes, to make sure there's nothing fundamentally broken. Now one might ask, why not run all the 40 tests? It takes a lot of time. In a given day, if you are doing a lot of the bigger teams are involved and a lot of changes, everybody running all the tests, it might end up consuming a lot of compute resources and licenses for the tools. So you run a subset of tests to make sure nothing is fundamentally broken, and you go ahead and commit the code. And then at every week level, you start running full regressions, which made up of all your tests, so like all 40 or 100, whatever. So whatever that has been passing so far, you run all of them and make sure that there is nothing broken. And if something is broken and you find the failing tests, you bucket them. Bucket them means group them by the common error signature, and you start doing the debugging of them and get them fixed before the new changes are being applied to the code. And then there are periodic releases. So as we talked about, there were various milestones. So for each of the milestones, to the backend design is released, where it is being synthesized and taken through the further activities. So those releases are done periodically, and those releases have different verification requirements to be satisfied. So that all happens as a part of the releases. And as we talked about, there are so many tests that we are running, and so much of interactive activity that takes place. So the resources like the compute, the licenses have to be optimized, and in order that is something that's also monitored as part of your regression phase, as to like how much memory is being utilized, how much compute power is utilized, and make sure that they are all optimally utilized is handled as a part of your regression phase. Along with these three phases, we have one more activity that we had not officially called out in the verification process, which is the management part of it. The management part of it involves tracking and making sure that things are progressing as per the the schedule requirements. The verification, one thing is it has to meet the requirements. Along with that, it's equally important that it meets requirements in time, right? That is also equally important. So we track, like for example, how much the test bench implementation is completed and how much test implementations are completed, and all this tracking happens with the help of the task list that we created as a part of the planning phase, right? And then we have to also track the various regression status, like how many tests have passed, failed, how many buckets are there, and then how many bugs have been filed, and then what are the coverage metrics. So all that are tracked along with the development phase type of metrics. So for each of the phases, a different set of metrics are being tracked as a part of the management work, and then various reports are created which gives the visibility to both the team as well as to the upper management, that how the verification is progressing. So each of so this is how the like the verification process that we had defined gets implemented when we start executing the project. So we were able to define the verification process, and we saw the implementation of it. And this slide quickly gives you a sense of how much time is invested in each of the phases, because we often tend to think as a new verification engineers that like we might be having the assumption or idea that it all is all about coding, right? There's a misnomer that a person might have. It's not true. So if we look at the overall verification activity division in terms of time slices, I know these are not like 100% accurate, but the proportions kind of remain same. In the planning, approximately 20% of the overall time is invested, wherein you come up with those three plans, and then test bench architecture and task list. About 20% you invest in planning, about 30% you invest in development of the test bench and the tests, and then remaining 50% is predominantly is like what is popularly known as R&D, right? Like it's a regression and debug. So you keep running the tests, and the test will fail, and you need to go find out why the test has failed. So we should not ignore building the debugging skills as well, along with the skills of building how to build the test bench. The key point that I wanted to make over here is that we should not think only coding is the end of the learning the verification. The one, we need to understand the planning process, and also we need to be really good at debugging part in order to like really be able to contribute to the overall closure of the verification project. A little bit in further details as to what happens in the planning phase. So in the planning phase, as we talked about, we are translating the requirements into verifiable descriptions, right? And it consists of building three plans: the test plan, checks plan, and coverage plan, and then using those plans to define the test bench architecture. So that's the most important thing. And this verifiable description, when we say, right, it is about defining series of stimulus, checks, and the coverage that we need to meet the requirements, right? And the functional coverage ensures that the scenario of interest has taken place, because we are talking about implementing the coverage driven constraint random verification approach. And in this approach, what happens is we are planning to generate a constraint random stimulus, and when we do that, we do not know if a particular scenario of interest would definitely get triggered, and in order to find that out, we also need to add the functional coverage to it. And now next we'll look into a details of what are these plans. So in the test plan, predominantly we focus on list of scenarios that we need to create, and any specific the test specific checks that needs to be implemented have to be included as a part of the test plan. And for the constraint random verification, along with the scenarios, we need to list the programmable parameters, right? Like for any given IP, there are a lot of registers that are provided which can be used to configure the functionality of a particular IP, and those are called as programmable parameters. So we need to make sure that whatever the scenario we are exercising in all possible programming, whatever the legal combinations of all possible programmable parameters, right? So those also have to be listed as a part of the test plan. And along with that, there could be programmable configuration. So what it means is that you could have, let's say, your mobile phone, and it could have a OTG USB port, right? And OTG means that a port could act both as a host as well as device. So now if I were to implement a simple data transfer test, then I have to run that test in both the modes, that I have to run the mobile port acting as host as well as the mobile port acting as a device. So that is the configuration. And so the difference between the configuration, like a programmable configuration and programmable parameters, is programmable parameters is something which can be changed during the course of execution of a test, and whereas the configuration is something that you program once at the beginning of the test, and then it remains same throughout the course of execution of test. So those have to be captured as a part of test plan. And in the coverage plan, especially when I say coverage plan over here, I am referring to functional coverage plan, and we will look into more details about these coverage metrics further as a part of this course. But in the coverage plan, we need to capture like some of the scenarios which are of which are of key interest, and to the overall requirements of the particular design, and any key combinations of the programmable parameters we need to capture as a part of the coverage plan. All the interesting scenarios and all the interesting configuration and programmable. So we might have hundreds of registers, but among them, whichever are key, which are important, that must be verified, which if we do not can cause a can cause a showstopper bug, or can affect the overall functionality of the design in a way that makes the chip unusable, right? So those we need to capture it as a part of the coverage plan. Obviously, so if you think theoretically, you want to capture everything, and obviously we do that. So the idea of building these plans is we need to think theoretically to be able to capture everything, but while we start executing it, we need to execute what is important. So that is one very important aspect of verification, that because of the infinite scope, although we capture everything in the plans, but when we start executing those plans, we have to prioritize to the key requirements that are out there. And in the checks plan, we need to capture the checks which are done globally across all the tests. If it is a test specific check, you capture it in the test plan, and if it is a global check that's applicable across all the tests, then those checks are captured as a part of the checks plan. And we also should mention the location where the check gets implemented, and all these three plans are expected to be indexed to your requirement specification, so that at any point of time, if someone says, for this particular section, subsection, for this particular requirement, how have you done the verification, we should be able to reference it back and tell that, okay, this part we are creating these scenarios, this is how we are covering, and this is the type of checks that we are implementing. Yeah, so we have looked at we are looking at more details of the verification planning phase, and we looked at how to create the plans, right? So the next step is we need to create the test bench architecture, and to create the test bench architecture, what we are essentially trying to do is we are trying to build like a model of the application world that surrounds the design. That is what we are trying to do. So what that means is, if I am verifying a mobile chip, then whatever that mobile chip is expected to undergo, let's say what happens when the call is received, what happens when I am recording a video. These are all the various scenarios, and these scenarios we need to create a view of the world around the design so that we can exercise these scenarios. Now here comes one of the challenging area, that to what level we need to model the application world around the design, right? That is a one very key question, because you don't want, because any design these days is a combination of a software and hardware. Now the application world that we are modeling around the design involves lot of software interaction as well, and you don't want to over model the software, as well as you don't want to like leave it out, right? So because if you leave it out, if you cut it too much, then you have a risk that you are not exercising the use cases, right? So but at the same time, if you keep modeling, then the model becomes too complicated, then the simulation cycles, it will take too many simulation cycles. So you have to find the right level of balance between them, and in order to do that, one of the principle that we need to use is the same principle, that we need to do the modeling uh, just enough to the extent that design sees it, right? So if something is not visible to design, then, and if it is only something that transparently happens to the design, then we don't need to model that part of the application view. So only the view that really matters to the design is what we need to model it in the test bench, and that part we need to keep in mind while we build the test bench architecture. And in order to build the test bench architecture, we need to understand two views of the test bench architecture. So one is this layered view, and another is a structural view, which we will look at subsequently. So in the layered view, what happens is the innermost circle is your DUT and its connection to the test bench, whatever the interface level, that connections that you do. The second level is consists of mainly, I mean, there are clocks and research generator, which is a small part of it. The key part is the bus functional model. So the bus functional model says to whatever the interfaces that you are hooked up, you are hooking it up at the signal levels, and those signal level in interactions that takes place with the design now needs to be converted into a transaction level. So that is the core essence of your second layer. So in the second layer, you are translating a signal level interaction to something that happens at the transaction level. And at the third level, what happens is it builds on the top of whatever the transaction level information that you have created, and it's called as like a translator. So in this one, what you are trying to do is you are taking a very high level stimulus that might be coming in, and you are translating that into a set of transactions, and those transactions can be taken by these BFMs and can be driven to the set of interface signals which the design understands. And there could be end-to-end checker type of a components that could exist in this layer, like scoreboards, which consume transactions that are happening at different interfaces, and they are checking to ensure that the functionality is met. But the point that you need to take over here is the theme is translators. That is, you are taking transaction and processing it transaction level, or translating from a higher level abstraction to the transaction level. And the fourth layer of it is you are essentially modeling the configurations, your state that exist in your test bench, and any controls to the stimulus that you can provide, and the functional coverage aspect of it, which essentially provide you the control on the the stimulus that you are creating, right? Your stimulus generation layer is part of your fourth layer. So you are able to create the stimulus and you are able to control the high level stimulus. So this stimulus, what we are talking about, is not a transaction level stimulus, but it is a much higher level stimulus that gets generated from the application. For example, for a USB, I could be saying, transfer like a transfer 10 kb, right? So now when I say transfer 10 kb, there are a lot of things that needs to happen for the 10 kb to be finally transferred on the wires. But the application view will look like transfer 10 kb, right? So you generate those bunch of transfer 10 kbs, then these translators translate that into a way that transaction level details of BFMs will take it and then program it into the DUT to execute that. And we need to generate different types of stimuluses, and in order to do that, the configuration and state come into play. We will look a little bit more closer into how these come into play in the structural view. And the last layer is a set of tests, right? So the tests uses all these inner layers to achieve the intended scenarios that we had defined it in the test plan. Now in the next slide, let's look at how these layers are translated into actual structure of implementation, right? So this is a typical test bench view. So let's start from the DUT, right? So if we look at it, we have a design, and you have every design is made up of a data path and a control path, and between these two you have this set of control and status registers that are present, which control both of these and which can be also programmed from your application. So, and for controlling the data path, you typically have a data interface, and typically, let's say you might have a AXI type of an interface for a data, and for control interface you could be using a APB, and then the rule of thumb is for each of these interfaces, now you need to provide one BFM. That's how you start off with the architecture, because from the signal level you need to convert it into a transaction level whenever you are building a test bench using the high level verification languages, right? And then on the top of BFM you have this app to transaction type of a translator, and so this one will convert your application level stimulus, as we talked about, into something that a BFM can understand, right? So, and this is an optional layer. It may be present, it may not be present, and that depends on like how complex stimulus that you are generating. If you are generating a very high level stimulus that the BFM cannot directly understand, then you need a translator. But if not, then probably you can get away with it. So then you have a high level the application level stimulus generator for each of these interfaces, and there could be some interfaces that could be just we just need to monitor it. Like let's say we have an interrupt interface, we are just monitoring it, so we may not be really generating any stimulus over there, or there could be some interfaces where we are monitoring and generating some sort of a response only whenever there is some activity coming out of a design. And for the data interface, we will be generating like let's say we are generating various transfers as a part of the data interface stimulus. And control interface stimulus is like, let's say I want to generate a intermediate reset, or I might want the design to go into a low power entry exit, or I might want to change the speed of some interface. So those are generated as a part of the control interface. And then typically between these two, like both the data interface as well as the control interface generators, you use this intermediate like a shared global configuration and state. So configuration, as we briefly talked about it, like what's the mode in which the DUT is behaving, and it in the context of test bench, it could be both like one-time programmable configuration as well that we can dynamically program. Those are present over here because ultimately the stimulus generation has to take whatever the program configuration into consideration before generating the stimulus, because it has to match the stimulus to the configuration that we have programmed. And state, like let's say we could have multiple low power states and we might have to go into them step by step. So we need to know the current state in order to generate what is the next state of stimulus that we can generate. And we also need the state for the like a data transfer generators to pause if the DUT is in a low power state. So we need that. So that is how the configuration and the state type of objects are utilized. And on the left side, if you look at it, right, so we have a data integrity scoreboard. So the data integrity scoreboards, what they will do is you would take the input from whatever the reference stimulus that we have applied, and then when the DUT transforms that whatever the stimulus that we have applied and generate some responses, and we collect it over here and we do the end-to-end matching to make sure that the intended functionality end-to-end is satisfied by this design. Because these BFMs will do the individual interface level checks. So this BFM will not be able to do the checks about what is happening on this side. So the end-to-end functionality of the design, whether it is satisfied or not, is taken care by your data integrity scoreboard. And functional coverage models will interact almost with all the parts of your test bench components. They collect all the information, and then they will utilize that to figure out whether all the configuration parameters have been exercised, all the programmable parameters have been exercised, the transitions have taken place, the various scenarios have been generated, the cross scenario interaction has taken place. All that is taken care by this functional coverage model, and it works by collecting information from all the test bench components. So this is how you build the structural view of a test bench. So now that we have created like a complete verification plan, that we have the three plans, we have the test bench architecture. Now let's say how, if we have to implement the test bench architecture using the HVLs, how do we go about doing that? Like if we were using only HDLs, right? Like if we were using pure Verilog or a VHDL, those were designed for modeling either RTL or a behavioral code. They were not they did not provide a lot of constructs that make the task of verification easy, right? But when we look at the high level verification languages like SystemVerilog, these are actually domain specific languages, and they have enhancements to ease the verification. And as we have looked at it, right, so we know that verification is all about generating stimulus and checks, right? So if we look closely in the HVLs, right, they provide special constructs in order to do that. So for handling the randomization, there is a constructs called constraints, and constraints enable you to generate like a pseudo random behavior, because you don't want pure random. Pure randomness is not useful. So the constructs like constraints enable you to generate the stimulus that is meaningful, right? Like a pseudo random stimulus that is meaningful. As we talked about, you want the stimulus to be generated as per the configuration that you have selected, as per the modeling or the programming of the DUT that you have done. So you want the stimulus, and yet within within whatever the configuration that you have programmed, whatever the variation that is possible, you would want the stimulus generation to be able to do that. And it also, as we looked at it, like a control stimulus has to be biased with the current state of the DUT. So all that modeling is done with the help of the constraints and the randomization features that are provided in the SystemVerilog. And then there is a construct called assertions, and assertions is an area by itself. Assertions are useful for both the dynamic simulation world as well as for the formal verification. So formal verification heavily relies on assertion. So assertions is also hard to pick it up, but if you pick up assertions, that will be useful for both the dynamic simulation as well as for the formal verification. So assertions are very useful when you want to do like either a interface level or a like a DUT based white box type of a checks, right? So anything signal level checks you can do very well using the assertions. In nutshell, assertions are modeling language for waveform. So you can represent any waveform, any complex waveform in a very compact, concise and correct format using the assertion. So once you have modeled the waveform, now either you can use that waveform for checking certain functionality or covering that particular functionality, which is mostly applicable for the simulation world. But in formal, you can use that waveform that you have modeled to tell the formal tool to generate the possible variations of the waveform characteristics that you have captured. So that is how the assertions becomes useful. However, assertions do not cover all the set of tests, all the set of checks that we need to do. For example, scoreboards are not implemented using assertions, right? For the scoreboards, we still use the behavioral modeling using the SystemVerilog code. And then there is this construct called functional coverage. So as we talked about briefly, we are generating a constraint random stimulus, and that could be covering a wide range of state space, and among that state space there could be few key important things that we want to make sure that it has must happen, that we can model it through the functional coverage, wherein we can check whether a particular variable value has taken all the possible values, and then in combination permutations with the other variables to cover all the configuration space scenarios, we can do the transition coverage. So these type of constructs which are present in HVL, they enable you to build the test bench much more easily. And while we do that, today's complex test benches, the reusability becomes very important. Reusability can come in the form of either we are reusing some part of the test bench code which is present within the organization, or we could be buying some verification IPs, for instance, from some third party big three vendors, right? So now how do we make that work together is all magic of the object orientation. And also these programming languages like SystemVerilog, they provide lot of assorted data types. So how do we use that? All of this gets used in order to realize the test bench architecture that we had talked about. And while we do that, we also follow the verification methodology. The methodology becomes very important because we want to have a repeatable way of doing things, right? So so as we have decided that we are going to build the test bench in a coverage driven constraint random verification. So what the industry has done is they have defined a framework in which this type of test benches can be built. And the advantages of this is that once we have created a test bench following this type of a framework, it is consistent across industry, right? So a new engineer comes into the company, it is very easy for him to understand, because he understands that the high level stimulus will be present in a sequence, the translators will be in a agent, and then the scoreboard will be present over here, and the driver for a particular interface will be present in a particular place. So everything becomes well structured. So on the top of that, these frameworks are not just theory, but these UVM type of frameworks are built using a set of base classes. And those base classes, you can think of it like an application forms, right? So it has, like, for example, name, address, mobile number, the standard values are printed, whereas whatever is a variable, that is something that you need to fill it in. So the overall framework is provided as a skeleton, and the rest of it, depending on whatever the verification that you are performing, you fill it in. And this type of base class libraries, when they are delivered, it makes sure that whatever the best known practices that are defined, it becomes easy to implement them, right? I just need not do something in a particular way, because now I am delivering you a base class library. When you extend it and use it, you have to do it in certain ways. To an extent, we can deploy all the best known practices and make sure that people do those things in a specific way, and this provides a lot of consistency and in the way we do things. portability because of the standard way of doing things. Now if we buy a third party component, it will be much easy to integrate. And the point to note over here is that all this is possible because the UVM is built on the top of SystemVerilog, which is object oriented language. So because of the object oriented nature of it, that we are able to build a methodology. Otherwise, building such a methodology which is theory plus the deployment of theory in the form of base classes is very hard if we have to do it with only with Verilog, right? And the key concept over here, as we have talked about, it's a transactor type of an approach. Don't take it in terms of like a verification methodology specific, but this is a key concept that you create a high level object and you process that and you transform that to something else, right? So that is the basic idea. And when you do it in that form, once you have captured something in the form of object, you can change the object and pass it to another one. It becomes very easy to send it. Like unlike if I had defined that as an argument to a task or function, then if I want to add one more new argument, I need to go change the definition of the task and function everywhere. Wherever it was defined and wherever it has called, I have to change everywhere. But when I do the same thing through an object, and if I change an object, I don't have to change the interfaces, for example, right? So that makes it easy. And so we use this verification methodology and the high level verification languages to realize the entire test bench that we had shown following the task list that was created as a part of the planning phase. That's the main activities that is done as a part of the development. So after you have developed a test bench wherein you have the test bench top where you have connected the DUT and you have connected all your test bench components together, and you have written few early tests, the next step is that you want to start compile, run and start debugging the test. So what you do is this phase part of the development where we had referred, if you remember in the overall implementation phase, like a scripting was one component of it. This is the phase where you employ a lot of make files, shell scripts, and like Python or a Perl scripts to optimize this phase. So so as a part of compile, these are all put as a targets in the make file, and you specify your test bench top and the various directories in which the test bench code and the RTL code is included, and the test bench is compiled, and if there are any compile errors, they would be shown in the compilation log. You would fix them, get it all compiling cleanly, and once it starts compiling cleanly, in terms of performing simulation, there are two modes that are available. There is an interactive mode and there is a batch mode. As a part of your early test bench bring up, you would use an interactive mode. In an interactive mode, you get the IDE, and then you can keep if you have used any standard interactive development tools, you know that you can put in a breakpoints and you can do a single step execution, and you can watch the values of variables. All this is possible in interactive simulation mode, which is typically used during the early phases of development, where you would want higher level of controllability and observability into the code that you are developing, and you can also look at the waves, and you can run a partial test simulation, like let's say your test total runtime is for whatever milliseconds, and you run it for 1 millisecond and look at what has happened, and then based on that you can run further in the interactive mode. And so that is useful while you are trying to bring up a part of your code. But once you have certain level of confidence in the code that you have built, you go into the batch mode. Batch mode is a mode in which your entire test bench is compiled into a single executable, and you use that executable to run multiple tests. So you have put in multiple tests and you compiled it all together, and now you want to run those tests in different flavors. and that's where you use the batch mode, wherein now you can launch all of those tests parallelly in your compute farm, and they will all complete parallelly. If you do not have the compute infrastructure, of course you can run it serially as well, but typically you want to run it parallel so that they complete quickly and you have the results available. So in essence, you use the interactive mode for your initial debug, and once the initial debug is up and running, and to run multiple tests together in the different flavors, you use the batch mode. And this running of multiple tests together is what forms the regression phase. So yeah, so we were discussing this batch mode is what forms the regression phase. So once you have about let's say 50 to 60% of your entire test suite ready, right, that's when you enter the regression mode. And in the regression mode, all that you are trying to now ensure is that the newer changes that are coming in are not affecting the the existing features. And then we need to periodically release the code to the backend, and when we are releasing that particular code to the backend, the quality of code is it has up to certain level that is required by that particular milestone, and that's ensured through the regression. And regression is primarily your running set of tests, you keep that in mind. And when you run those tests, invariably when the code starts changing, the tests that were passing before will start failing, and the total number of failures starts accumulating, and those needs to be fixed. And after fixing, again you need to rerun those set of tests to make sure that again the full test suite is passing. And then you break up this test suite into different set of test suite to manage different configurations, or you could be performing like a subset of tests, you could be taking and performing a low power simulations on those. What you are trying to do is you are trying to take this bunch of tests and make sure that you run them in all the flavors, keep the passing tests in the passing state, run any low power simulations that are required on a subset of these particular tests, and you ensure that the run times of these particular regressions are sort of in check, and whatever the releases that needs to happen, the required criteria of passing tests is met, and ensure that the total number of failures that are getting created are not accumulating too much, affecting the code quality. That's what is the sort of the focus of your regression phase. And while doing that, keep improving the pass percentage, right? So that's what you are trying to target in the regression phase. And the bulk of the activity that is performed during the regression phase is debugging, and we have to treat the debugging as a like is like debugging is like being detective, and you look at various clues to eliminate the suspects. That is a process that you follow. And the failures happen because of unmet expectations, and this could be due to your requirements misunderstanding could be there, or there could be programming errors in the design, or there could be operational environment issues as well, that we are not using the right version of library, or the right version of tool is not being used, or we are not picking up certain version of code correctly. So those type of operational environment issues could also be there, and all these issues will predominantly lead to failures. And the process of debugging generally for the verification engineer starts with the log files. You look at the log file to understand what stimulus the test has generated, because for the constraint random test, the one key thing is that the stimulus generated will not remain fixed. So unlike directed test cases, your stimulus generated is fixed in nature. So you can always correlate your test code to the log file, and they will all correlate one on one. But when you do the constraint random simulation, constraint random test simulation, you might have put a for loop, and inside that you are randomizing a particular scenario. The what type of scenario that it is going to generate is not defined. So that is something that when a test fails, first step is that you figure out what scenario has been generated using the log files, and then you look at the activity between the interface between the test bench and DUT to figure out whether the problem is with the test bench or with the design. And if the problem is with design, typically you go more deeper using the waveforms, as an approach to figure out where things have gone wrong. And if the problem appears to be with the test bench, then you go deeper into the test bench. And sometimes you can again use the interactive debuggers as well to figure out where things have went wrong in the test bench. And once you have discovered the bugs, you file the bugs, and then if there's design bug, the design team will take care of fixing that bug. And after the bug is fixed, you will be rerunning the test to make sure that it passes again. And this is a very important activity. And if it is a test bench bug, sometimes even for the test bench there are tracking bugs that are filed, and if the different person or a different team within the verification team needs to fix it, and then you follow through the same process that the bug fixed from a different team, and you rerun the test to make sure that it passes again. See, you perform like, let's say all the failing tests are debugged, and then you have a good pass percentage, and then there comes a point when you have to say that the verification is done, and but in reality verification it never really completes. So all that you are trying to do is you are trying to minimize the risk of any chip that you are building. And the way you minimize the risk is you use different set of metrics to help you figure out that has the verification reached the level of maturity that we can tape out this particular chip, right? So typically you rely on code coverage, like it should be 100% code covered. Code coverage should be done. And here also what happens is it may not really become 100%, so you have to judge a few code coverage holes, whether they are really relevant. If they are not relevant, then you can waive them. So that's why the judged code coverage should be 100%. Similarly, for the functional coverage, it should be 100% functional coverage. And then your all directed tests should be passing. Directed test should be 100% passing. That's very important. And then the random, whatever the random test that you are running, you could be running it with different seeds. Ideally, you would want to have a zero failures, but then what you do is it may not converge to really zero failure. So you decide on that there is an acceptable failure rate depending on the different types of project that number gets defined. And then if that acceptable failure rate is available over a few weeks, then you say that yeah, that's a good enough criteria for us to say that this has achieved the necessary stability. And then also you look at certain level of history for past few weeks to make sure that there are no critical bugs found. What's the rate of bugs that we have found? And then you check whether all your critical power and performance goals are they all met. And using all these metrics, you kind of arrive at a conclusion that we have met the necessary verification quality criteria that we can now tape out this particular chip. That's how the sign off happens. And sign off is the sort of the final phase of our verification process. So we have looked at a lot of technical aspects as a human aspect as well, and this is the how typically the verification teams are composed. The central to the verification team is a verification manager who coordinates all the team. And the point to note over here is that these roles that we are defining, there could be a possibility that in a smaller setup or a lower complexity design, a single person could be playing multiple of these roles. Or for a very complex design in a bigger organization, a single role could be played by multiple people. So those combinations always exist, and this gives you an idea that what are the areas that you need to master. So there's always a specification experts who understands the requirement very well, and typically there will be one person like in the architecture team as well as in the design team as well as in the verification team who understands all the requirement specification very well. And although everyone is expected to know the requirement specifications, but invariably you have one person who understands this very well, and that person will be go-to person whenever there is a some ambiguity is there, or some requirement where there is a contesting that is going on, that somebody thinks in one way, another person thinks in another way. So the specification expert is a person who resolves it. And then there's a verification expert. So verification expert understands the high level verification methodologies, methodologies, high level verification languages, the verification methodologies, various tools. He understands those aspects very well and helps pick up the right set of flows and the right type of tips and techniques that we need to utilize. And he is the guy who generally ends up writing verification plan, and he will create the test bench architecture, and he will primarily sort of play like a lead type of a role in the overall verification project execution. And you will have one guy who is an automation expert, and we have seen that in verification there are a lot of things that are very repeatable in nature. So for all those repeatable things to be executed efficiently, we need a guy who automates them, and it could be your make file flows, it could be test bench generation flows, it could be your regression management, or it could be failure bucketing and the failure assignments, and it could be extracting various metrics from various internal systems. All those come under purview of this automation expert. And this guy generally has a very good handle on Linux, has a very good handle on the scripting that is required, and understands various tools and utilities that are available to make that happen. And then you have the verification engineers, the early stage verification engineers, who are the working horses, who implement and who understand specifications and who understand test bench architecture, and they take the architecture that is given by the verification expert and they help implement it, right? So they have a good language command over SystemVerilog, and they understand the UVM type of a methodology fairly well. And when they are asked to implement a particular component, let's say an agent or a scoreboard, they understand what that means, and they also understand how to run the tests around them, and then go through, if there's something is failing, go through the debug process to isolate the issue. If there's a test bench issue, fix them. So that is what is the expectation from the verification engineer. And the role of verification manager is mainly providing clarity to the team as to what exactly needs to be done for the next milestone, and any prioritization that needs to be done, and any cross coordination that needs to happen within the team, and as well as across the other teams for which the verification team is responsible for delivering, happens all through the verification manager. And as a part of your verification career as well, you will of course go through each of these roles as you grow further in your career. So far we have talked a lot about functional verification, but there are other types of verification that are done as well. There is a performance verification wherein we predominantly measure the performance metrics, which are like latency and bandwidths, and for the, at least for the protocol type of designs, the different type of designs have different type of performance metrics, and performance is equally important as functionality. And the test bench that is created by the functional verification team is also used for the performance verification. So performance verification, typically what they do is they create certain specialized test cases, and they also provide additional instrumentation within the functional test bench to extract the performance metrics, to check whether it has met the necessary requirements. So they run their own set of regressions, and to check that whether the performance targets are met. And then typically these days, if there is a lot of power constraints, if it is going in a mobile type of a devices, and the design is going in mobile or a very power constrained type of designs, and like a lot of low power techniques are used. They use multiple power islands, and then different voltage levels are being utilized, and those also needs to be like, and then the power domains could power up and power down. All that needs to be, that can be simulated, that when one particular power island has been turned off, and the rest of the design, whether can it function properly or not. Those guys also use the test bench that is built by the functional verification team, and they run selective test benches which could power on or power off certain islands to see whether still the functionality remains intact, and there are ways to also do some approximations about how much power it is being consumed. So all that comes under the power verification purview. And these days, with the growth of usage of silicon in automotive sector, the safety verification has become very important. And as a part of safety verification, what they try to check is that if a design develops some sort of a flaw due to usage over a period of time, can we detect that flaw and report it, and then put some redundancy such that if there is one part of the design misbehaving, can it switch over to another one to make sure that there's no critical failure for the critical parts of the logic. So there is a safety verification, and safety verification has its own flows. Again, they utilize the test bench that is built by the functional verification team to perform the safety verification. And with the growth in the data center, the silicon usage in the data center, the security verification has become another important area. You don't want some hacker to get access to even the wires of a particular chip and being able to hack through and find out steal some critical information that is there are many authentication mechanisms now based on the hardware rather than only software, because software only mechanisms are easy to break. So those are being verified through the security verification, which again can utilize the test bench built by the functional verification team. Apart from these different dimensions which are sort of parallel to each other, there is also this is a horizontal, right? So you have functional, performance, power, safety, security. These are all sort of horizontally different one. There's also vertically that you have a block that you have verified, and then what you do is in the SOC you divide the overall SOC in different partitions. There could be like a IO subsystem which connects all your peripheral type of a devices. You could have UART, SPIs, PCI, USB type of a group of systems, and then you have your memory controllers that could become a memory subsystem. Then you have multiple CPU cores that could become a CPU subsystems. So all these subsystems are created separately. So you initially verify each block of them and then put some of these together, and then let's say I verify IO subsystem, memory subsystem separately, CPU subsystem separately. So that is your subsystem level verification that takes place, and then put all of them together, and then you create the final chip that you are going to tape out, and then you perform the SOC level simulation. And across all these vertical abstraction, you want to reuse things that what you have built at IP level, part of it you want to use it at subsystem level, and then part of it you want to use it at the SOC level. So how do you do that? That's again the area that is dealt by the verification architecture. So these are the few like the horizontal as well as the vertical dimensions that are part of doing the functional verification of any latest ASICs. In terms of verification trends, there are different technologies now that are available that can be utilized for performing the verification, and we are going to predominantly focus on this coverage driven constraint random verification. It's also called as like what we do is part of the dynamic simulation based verification. And here, as a part of industry, as we have seen the trends as well, the high level verification language that we use is SystemVerilog, and for SystemVerilog the reference is the IEEE's LRM. That's the main reference. I think everyone should definitely get that. We will look into more details as we go in the further sessions. And the verification methodology that is being used is the universal verification methodology, or the UVM. And for the UVM you have the set of base classes. The base class reference, we can use it from the Accelera. They also provide the source code. Everyone should download the UVM source code. I think the latest version probably is 1.2. We should definitely download that and have a look at it. So the coverage driven constraint random verification, I am not going to discuss a lot about it over here because we already discussed a bit and in future I think we are going to dig a lot more deeper into it. The second one, which also called as this is the dynamic, this is static verification, is performed also called as formal verification. So formal verification is gaining a lot of prominence in terms of like wherever you have the compute, it's for a specific areas. Like if there is a lot of compute intensive type of a design that exists, especially for microprocessor verification, it's gaining a lot more traction because there you want to prove the absence of bugs in the data path. Like for example, all of us know how costly the floating point bug that the Intel processor had so long time ago, right? So Pentium processors had long time ago. So we, for anything compute, the formal verification works very well. Data path type of a verification. For control path type of verification also now formal is being employed, but formal it is little hard to learn and apply, and it had the scaling issues that for a very complex design it was not able to converge. Those issues still exist, but to a large extent I think the companies, EDA companies, have fixed them, and this is getting utilized in few specific areas, and the scope has expanded. And the formal verification, one overlap that we are going to have is the assertions part that we are going to learn in SystemVerilog. It is required for the formal verification. So I think we should learn that well, so that we can you have the opportunity to either do the formal as well as the coverage driven constraint random verification. And in terms of this dynamic simulation, the new thing that's happening is something called portable stimulus. So portable stimulus, as we saw that in the vertical reuse, that we had IP, we have subsystem, and then we have the SOC level. Now that reuse, how to make that reuse much more easy, that you develop one stimulus model, and that stimulus model, how can I target it to all these level of abstraction, and even going up to silicon, right? So how do we do that? Not only you do it for the simulation, within simulation you do IP, subsystem, SOC, and then you do emulation, and then you do the silicon, right? So how do we kind of use the same stimulus for all of them? There's a new standard that's coming up. A new means, I mean, it's there for the industry for a while, but I think the slowly the adoption is growing in the form of a portable stimulus. And as the size of ASICs are growing, the simulation is kind of hitting the wall. It takes very long time to run tests on the complex designs, especially at the SOC level. So there is an emulation being used. The emulation is being used. Emulation is performed through some specialized hardware, the additional hardware that the companies needs to purchase from the EDA vendors to perform the emulation. So emulation could be used for either increasing the simulation speed, or you can emulate the entire SOC so that the software development can start early. Some of the emulators that I know of are like the popular ones is Synopsys, Zebu, Cadence, Palladium, Mentors, Veloce. They can help you run your test benches faster, or you can put an entire design, and you can also start doing an early software development to the extent that even for some of the SOCs people are able to boot the operating systems on that. And the other thing is the automation. The automation is happening in the two areas that I know of. One is the test bench generation. So a lot of tools and utilities are being provided that can quickly help you generate the test benches. And as we saw that in the overall chip design cycle, we were spending at least about 50% of time in regression and debug, and within that regression and debug phase that we are performing for 50%, about 70% of that is debugging, as we talked about. So there's a lot of scope to improve the debug automation. So that's another area that is developing. So this concludes this session of overview of verification, and if I quickly summarize it, we connected to one of the areas that all of us have experienced in the form of like how have we done verification, and there's something that everyone has done the verification. We use that concept to build it further, to define and formalize a process of verification, and then we looked little deeper into the process of verification, where we identified those three phases. We have a planning phase, we have development phase, and we have the regression and debug phase. and then we looked at how do we implement that particular verification process and what is involved in implementing them, and we went one level deeper into like what's involved in planning phase, what's involved in the development phase, and what's involved in the regression and debug phase. And these concepts are very important, and what we are going to do in the next few sessions is we will apply these concepts now, really take a small examples and apply these each of these processes to see how they work, and put them into the practice. So I hope this readies you to get into applying. I hope the concepts are clear and it readies you into applying this into the real life examples. Thank you.